At the moment an Airbus A380 leaves the ground, something happens that should not be possible. 590 tons of metal, fuel, cargo and human beings, the weight of roughly 80 adult elephants, lifts into the air on nothing but the movement of invisible gas. No wire, no support, no surface beneath it. A century ago, some of the most respected scientists and mathematicians alive looked at the numbers and concluded that aircraft of this size were fundamentally impossible. The wing area, they calculated, was simply not large enough to lift such a weight. Physics would not allow it. They were wrong. But understanding exactly why they were wrong, and what is actually happening in those seconds between the wheels leaving the runway and the aircraft climbing through the clouds, is one of the most extraordinary stories in all of engineering, because a 500-ton aircraft does not fight gravity to stay in the air. It uses something far more elegant than that. Before we explain how it flies, we need to understand what we are actually asking physics to lift. A fully loaded Boeing 747 weighs approximately 412 tons at takeoff. An Airbus A380, the largest passenger aircraft ever built, weighs up to 575 tons. To make that weight feel real, a kilometre-long chain of 250 average passenger cars has roughly the same mass as a fully loaded wide-body jet, and a significant portion of that weight is fuel alone. A long-haul 747 carries up to 180,000 litres of jet fuel at takeoff. That fuel weighs approximately 150 tons, more than a third of the aircraft's total mass. The aircraft is, in a very real sense, a flying fuel tank with wings and seats attached. Now here is what makes this even more remarkable. As the flight progresses, that fuel burns off. A 747 flying from London to Sydney burns roughly 150 tons of fuel over the journey, which means the aircraft landing in Sydney is dramatically lighter than the one that took off from London. The wings, the engines, the control surfaces, all of them are designed to manage not just one fixed weight, but a continuously changing one. The aerodynamics that work at maximum takeoff weight must still function perfectly when the aircraft is nearly empty. That engineering challenge alone occupied some of the greatest minds of the 20th century for decades. Most people learn the same explanation for how wings work in school. Air travels faster over the curved top of the wing than along the flat bottom. Faster air means lower pressure. Lower pressure above means higher pressure below. The wing gets pushed upward. That explanation is not wrong, but it is incomplete. And the part it leaves out is what actually explains how 500 tons gets off the ground. The full picture involves something called angle of attack. A wing does not just passively redirect air over its curved surface. It is tilted slightly upward at the front, typically by a few degrees during takeoff. This angle forces the wing to deflect a massive volume of air downward as the aircraft moves forward. Here is the physics that matters. For every action there is an equal and opposite reaction. Forcing hundreds of thousands of kilograms of air downward, every second produces an equal upward force on the wing. This is not a gentle lift. It is a continuous, violent redirection of an enormous mass of air. At takeoff speed, a large jet engine moves a volume of air comparable to filling an entire football stadium every few seconds. The wing is working with that airflow, using both the pressure differential and the deflection force simultaneously. The result is lift, not from magic, not from defying physics, but from exploiting two separate physical phenomena at exactly the same time, at exactly the right speed, with wings engineered to generate the precise forces needed for that exact aircraft weight. The scientists who said it was impossible were calculating for wings that worked on pressure differential alone. They were not accounting for the full picture. Now here is something that surprises almost everyone who sees it for the first time. Aircraft wings are not rigid. They are deliberately designed to bend. In structural certification tests, the wings of a large commercial aircraft are loaded until the wingtips deflect upward by as much as 5 to 7 meters from their resting position. The test continues until the structure either passes or fails. On the Boeing 787, the wings were bent upward by over 7 meters before the test was stopped. The structure had not failed. This flexibility is not a flaw. It is one of the most critical safety features on the aircraft. A completely rigid wing would behave like a metal bar in turbulence. Every sudden change in airflow would transmit its full force directly into the fuselage and the passengers inside. More critically, a rigid wing hit by a severe gust load would have nowhere for that energy to go. It would concentrate at the weakest point and potentially fracture. A flexible wing absorbs that energy. The wingtip deflects upward, storing the energy like a spring. then releases it gradually as the gust passes. What passengers feel as mild turbulence would, in a rigid aircraft, be a violent structural event. Modern wings are built from combinations of aluminum alloys, titanium, and increasingly carbon fiber composite materials, each chosen because they combine high strength with controlled flexibility. The wing is not fighting the air, it is moving with it. Even with perfect wing design, none of this works without speed, and speed comes from the engines. A modern turbofan engine on an aircraft like the Boeing 777 produces around 110,000 pounds of thrust per engine. The aircraft has two of them. At full takeoff power, the combined thrust is roughly equivalent to 150,000 horsepower, accelerating a 500,000 kilogram machine from 0 to 290 kilometers per hour in under 40 seconds. During that acceleration run, the flight crew is tracking 3 specific speeds that every commercial pilot memorizes and monitors continuously. The first is V1, the decision speed. Before V1, if something goes wrong, the aircraft can still stop on the remaining runway. After V1, stopping is no longer an option. The aircraft is committed to flight regardless of what happens next. This is the point of no return. The second is VR, rotation speed. This is the exact moment the pilot pulls back on the controls, raising the nose and increasing the wing's angle of attack to generate the full lift force needed to leave the ground. The third is V2, the minimum safe climb speed. Even if one engine fails at this moment, the aircraft has enough speed and lift to continue climbing safely. These 3 numbers are calculated fresh for every single takeoff, based on the aircraft's exact weight that day, the runway length, the temperature, the altitude of the airport, and the wind direction. They are never the same twice. The margin between flying and not flying is calculated to within meters and seconds every time. Takeoff is only half the engineering story. Landing presents an entirely different problem. To generate lift, a wing needs speed. At cruising altitude, a 747 flies at around 900 km per hour. But a runway approach speed is closer to 270 km per hour, less than a third of cruise speed. At that reduced speed, a wing designed for cruise would generate almost no lift at all. The aircraft would simply fall out of the sky on approach. The solution is one of the most elegant pieces of mechanical engineering on the entire aircraft, the high lift system. As the aircraft slows for approach, the pilot deploys a series of movable surfaces that physically transform the shape and size of the wing. Flaps extend from the trailing edge, increasing the wing's surface area and changing its curvature. Slats slide forward from the leading edge, creating a new airflow path that keeps the air attached to the wing surface at low speeds. Together, these devices increase the wing's lift capacity by as much as 80%, compared to the clean cruise configuration. The wing that lands the aircraft is physically a different shape from the wing that flew at 35,000 feet. It is larger, more curved, and generates its lift through a completely different aerodynamic regime. This transformation happens automatically, controlled by hydraulic systems, on every single approach. Passengers rarely think about it, but without it, commercial aviation at the speeds and weights it operates today would be impossible. So here is what is actually happening when a 500-ton aircraft leaves the ground. 2 physical forces, pressure differential and momentum deflection, combine to generate a lift force large enough to overcome the weight of a small city block. Wings built from materials that bend rather than break absorb the energy of every gust and thermal without transmitting it to the passengers inside. Engines generating 150,000 horsepower accelerate the aircraft to a precisely calculated speed at which physics transitions from resistance to cooperation. And as the aircraft slows for landing, the wing physically transforms itself into a different aerodynamic shape to maintain that cooperation at a fraction of cruise speed. None of this is a victory over nature, it is a negotiation with it, one that engineers have been refining for just over 100 years. The air is not empty space that the aircraft pushes through. At speed, it becomes a medium as structured and supportive as the ground beneath a train. The aircraft does not fly despite the air, it flies because of it. Here is what I want you to think about after this video. Everything we just described, the lift, the flex, the flap deployment, is happening simultaneously, automatically, on thousands of aircraft right now. Most of them are over oceans, many are in weather that you would not want to drive a car in. And the failure rate of commercial aviation is so low that that you are statistically safer in that 500-ton aircraft at 35,000 feet than you were driving to the airport. How did engineering get that good? And where are the limits? That is the next video. I will see you there.